Let us now compute the maximum likelihood estimator for a geometric distribution. So the parameter for a geometric distribution is P, and this is what we want to compute. We want an estimator for P. So what is P? The P is the probability of success. So say you carry out n trials, and in these n trials there are s successes. So now you form the likelihood function. In the likelihood function you multiply all the probabilities together. So you have s successes. P is the probability of success, so p to the power of s, that means you have multiplied p s times. Now if you had s successes, that means you had n minus s failures, and 1 minus p is the probability of failure. If p is the probability of success, 1 minus p is the probability of failure. So you multiply all the failures. Then you transform this into log likelihood by just taking log of both sides. So log of L is equal to s log p plus n minus s log of 1 minus p. So now you take its a derivative with respect to p, because p is the estimator you have to compute. So dl by dp, and the first order condition is that dl by dp you set it equal to 0. So you take the derivative of this with respect to p, you get s doesn't have p in it, so you have s by p. And first note that d by dp of log p is 1 by p, and d by dp of log of 1 minus p is equal to 1 over 1 minus p, and then you have d by dp of minus p, which is minus 1. So this is minus 1. So you have minus 1 over 1 minus p, and that's exactly what you use here. S by p minus n minus s over 1 minus p equals to 0. So now you can rearrange this. So this becomes s by p is equal to n minus s over 1 minus p. Now this further becomes 1 minus p by p is equal to n minus s by s. Now you add 1 to both sides. This will give you p plus 1 minus p by p, which is equal to n minus s plus s by s. So now you just do the cancellations. This gives you exactly np is equal to s. So this s is equal to n times p, and from here you compute p is equal to s by n. So total number of successes divided by the number of trials gives you the probability of success. So if you had s successes in n trials, p is s by n. So for example, if you carry out 20 trials and you had 11 successes, then p will be equal to 11 by 20. So this is the number of trials, this is the number of successes. So this is the estimator in geometric distribution. Now we talk about the Poisson distribution. Now the Poisson distribution, the estimator is lambda. So again you have a bunch of observations here. So your observations are, say, n observations, x1, x2, x3 and so on. So you have n observations or n trials. Now you fit in each and every of these n observations, just like here we fitted in n observations. We fit in n observations here. So this is our Poisson distribution for each of these observations. Then you take the log. So I'm taking log for this product becomes sum. And notice that I'm only focusing on the numerator. I've forgotten about the denominator. I could have also taken here the denominator, but we will come to the reason why I have forgotten the denominator. So the reason is there is no lambda in the denominator, and we will come back to this later why we have dropped it. So you take log, just focus on the numerator, log of exponential of minus lambda plus xi times log of lambda. So log and exponential cancel out, minus lambda you sum it n times, this I goes from 1 to n because there are n observations. So this product also goes from 1 to n because there are n observations. So lambda you sum up n times, you get minus n lambda. Here log lambda is constant, it comes out, and you are summing up all the xi's. Again there is a term which is missing here, which is log of xi factorial. Now why I dropped that term is that you have to take a derivative now. So you have to take a derivative of, so I'm writing dl by d lambda. This correctly should be d of log L by d lambda, but anyway it does not matter. So dl by d lambda has to be set equal to 0. So this third term here, which would be log of xi factorial, does not have lambda. So when you take a derivative, that term will become 0, and that's why I dropped it here and dropped it here. So you have this. So you have minus n plus 1 by lambda. You have summation this, set it equal to 0. Lambda becomes the average of the values, 1 by n of sum of all the values. So I goes from 1 to n. So average of your observations is your estimator lambda. So the parameter lambda which you wanted to find out, its estimator is, you can call it lambda hat, is the average value of all your observations. You sum up all the observations, which are n observations, and you divide it by n. So in both these cases, we have number one, we are taking dl by dp here, dl by d lambda. Essentially we are taking derivative of the log, and you have to notice that the log does not change the maxima or the minima. The second thing is, we have not checked the second order condition. So you have to again take a derivative and check the second order condition, that the second order condition holds for the maxima. So for the second order condition has to be negative. So that you can check by yourself. But this is a good example to know how to compute maximum likelihood estimators using simple calculus.